you hit the recording too, over the weekend. A headline caught my eye that I thought you all could relate to. Just a second here, let me drag this over. This is the most boring person in the world, works in data analysis, likes watching TV, and lives in a town, scientists say. It's me. I won. I am the most boring person in the world. And unless there's any doubt, I kept reading, and it says that the other hobbies that were voted most boring, sleeping. I love to sleep too. So yeah, this is my new award. I am officially the most boring person in the world. And you know, you keep working in data analysis and liking TV, eventually you can get to the point where I am today, which is to use TV in our lecture today. I have an example based on one of my favorite TV shows. So merging my hobbies, my nerddom, and my boringness all into one just wonderful sphere. But yeah, you too can aspire to be boring and apparently hang out at an airport. I guess that's what boring people do. It seems like that would be pretty exciting to me, but who knows? So, anywho, we have a new topic to start today. Entering the world of what would normally be called multiple linear regression, meaning multiple predictors at the same time. So the idea of looking at what is the contribution of a predictor variable in conjunction with others, and to what extent does its effect change after controlling for predictors that are related to it. So that's the place that we have to go to. So anything that you want to talk about before we dive back in to new stuff? Any review topics or questions, concerns, boring hobbies you want to share? Okay, fair enough. Then away we go. So lecture 4 here we have to do. So even though you said you didn't have anything to review, I thought people would want to review, so I made you some review slides. Because it's Tuesday, and we haven't talked about this stuff in like 5 days, so you know, it may go away. So where we've been thus far, specific info for fixed effects. So fixed effects, more generally speaking, is a term that means constants estimated by the model. We have a fixed intercept as one type, and fixed slopes as the other type. So just reviewing a little bit of vocabulary there. And the role of any given predictor variable, which in my notation is always going to be an x, in creating a custom expected outcome, which in my notation is always going to be a y, is described using one or more fixed slopes. So the question of how many slopes do you need to describe the effect of a predictor depends on what type of effect it has and what type of predictor it is. So if you have a quantitative predictor, and it has only a linear relationship to the outcome, one slope is enough to capture that. The same is true if you have a binary predictor, 2 possible categories. There's only one difference between them. So the only kind of slope that you can have for a binary predictor is a linear slope. Hello! And to capture a linear effect, like I said, quantitative is just 1. You can also mimic an exponential curve if you take the natural log of the predictor and fit a linear slope of that. Otherwise, meaning most of the time, a predictor would need more than one slope to describe, say, nonlinear effects of a quantitative predictor, such as quadratic effects, which you got to practice in your last homework, or for categorical predictors that have more than 2 groups. So more generally, if a categorical predictor has capital C categories, we need C-1 slopes beyond the fixed intercept to differentiate all possible category levels with respect to the predicted outcome. And so for each of these fixed slopes, then, we're used to looking at what I would refer to as an unstandardized solution, meaning the answers in the metrics of the variables originally without transformation. And we get an estimate, which is the best guess given our sample data for what the slope's supposed to be. We get a standard error, SE here, which is the expected inconsistency, how far off on average the slope is going to be from the population slope. Estimate divided by standard error gives us our t-value, or t-test statistic. And from that, we get our p-value, which is the probability of observing a slope that big if the null hypothesis were true. And so we can use that information directly to make an assessment of significance relative to a null hypothesis of 0. And then, because significance is a function of both effect size and sample size, we need to make sure that we can describe the size of an effect, such as by taking our t-test statistic and converting it into an R or a D, which are both known as partial effect sizes when you have more than one predictor in the model. More about that today. All right. So any questions on the concepts on this slide to start with? And Zoomers, as always, I'm watching the chat window, so don't be shy. No? Good so far? Good. All right. Rocking on. So then reviewing definitions of fixed effects, let's say that I have this model right here, where I have one predictor, which I've labeled generically x1. So I have beta 0 as my fixed intercept. That's always the expected outcome when your predictors are 0. So in this context, it's when x1 is 0 specifically, because that's all that's in the model. A few of you I noticed on homework were missing questions about that, what the intercept means. It's only conditional on the predictors that are in the model currently. So if there's predictors that are not in the model, the intercept is not conditional on those, even if they're in the data set. It's all about what's in the model. And up to this point in your homework, you've had only one conceptual predictor in the model at a time. Potentially, it takes more than one slope to describe its effect, but like conceptually, there's only one variable. So then beta 1 is the slope, rise over run, change in y per unit change in x, the difference in the outcome per 1 unit difference. So if it's a quantitative variable, then we would interpret this in units of whatever the variable is, like per year, per pound, per whatever. If it's a binary predictor, then we only have one possible 1 unit difference, and we would talk about the slope as saying how the 1 group differs from the 0 group specifically, in that order. And if I only have one predictor, then I've kind of wasted my time doing a general linear model, because the slope could be more directly characterized as just the equivalent of the Pearson correlation. So the standardized slope that we would get from transforming our variables to a z-score metric, where 0 is mean, and, no, mean is 0, there we go, and standard deviation is 1, is equivalent to a Pearson correlation. But anytime you get more complicated with respect to what kind of predictors you want to look at, Pearson's correlation is not going to be adequate. And E in this case, E is always a residual, or a discrepancy, or leftover. It's the difference between y as it actually is and y hat that's predicted from your fixed effects. And E is where each person's observation deviates from the regression line created by x1 specifically. Now, if we fit a separate model that has a different predictor in it, for instance, x2, some other variable, everything is interpreted the same way, except now it's specific to x2. So the intercept is when x2 is 0. The slope is the change in y per unit change in x2. And E is the deviation of each y from the regression line predicted by x2. So this is what we've done so far. Look at one predictor at a time, describe its effects. If we have a predictor variable that requires more than one slope to describe its effects, then in addition to paying attention to what happens per slope, we want to pay attention to how the slopes work together to create an overall prediction. So that is answered in terms of whether the prediction is significant with our friend the F test. So the pieces of F is a ratio. What it boils down to is a test of what you know over what you don't know, meaning how much of the variability is attributed to the predictor variable slopes relative to how much is yet to be predicted. And F is per slope, which means that you can have a bad F if you have a model with 4 slopes, but only 1 is any good. So the weighting part of that is important to keep in the back of your head. So that's our test statistic for a set of multiple slopes, whether or not they significantly predict the outcome when you put them all together. And we have an effect size that goes with that, which is our friend R squared. So R square is computed using sums of squares. So sums of squares you can think of as information. It's the numerator of any of the variance equations. So the total amount of information to be captured in the outcome minus the amount of information that's remaining after the model has its say, so residual, remaining, leftover, you can think of those words, error is another one, divided by the total. That gives us R square. So you can think of R square two different ways. It is the square of the correlation between the outcome y hat predicted by the model and the real one. It's also the proportion reduction in residual variance relative to the empty model. So if we look at this equation right here, SS total minus SS residual, if you're in the empty model, how many predictors are in your model? 0. Yeah, not a trick. This is a review. So SS total and SS residual would be the same thing. If there's no predictors, if all you have is intercept, then you're at SS total. So this R square would be 0 in the empty model to the extent that you put in a predictor variable whose slope is useful, is not 0, then sum of SS total goes away, becomes SS model instead, and SS residual is what's left. So if your model is perfect, then you would have no residual variance left, and you would end up with an R square of 1. And there's also an adjusted version that is going to show back up today, by the way, where they are trying to get a better estimate of R square for use in smaller samples. So think of it this way. Why motivating this? Let's say that I had a sample with only 2 people in it. Could I do that? Sure I could, right? I can do anything I want. Now let's say that I have 2 data points and I want to draw a slope through them. How well is that slope going to fit those 2 data points? Perfectly, right? 2 points make a line. What about 3 people? Is it going to fit perfectly anymore? Not necessarily. It'll be off a little bit. 4 people, off a little more. 5 people, off a little more. So the fewer people you have, the easier it is to have an R square that's higher, and it's sort of artificial as a function of there's just not enough information to separate the slope from the error around it. So adjusted R square is a way to get a better estimate of R square for use in smaller samples. It's computed using the original R square that you would get from this formula with the function of n and degrees of freedom here. Another way that you can think of it is that it is looking at the change in the residual variance across models directly. So if you were to stick with me and take classes, say, on multi-level models, this is how we're going to do R squares in those classes, is literally see what's the residual variance, how much did it go down, because sums of squares stops being a thing once you leave this class. Once we get to more complicated models, then sums of squares is not how we estimate them. We use something called maximum likelihood instead. So this idea generalizes past this particular context. And if we only have one fixed slope, we don't need to do any of this, because if we only had one slope, the t test statistic for that slope is the same thing as the f for the model. And if I take that slope and convert it into a standardized slope, that's Pearson correlation, and that Pearson correlation R, if I square it, is the model R square. So this extra step of f in R square is only needed if you have more than one slope in the model. So where we have been thus far, we fit models that have more than one slope. But in each case, they were slopes that work together to describe the effect of one variable conceptually. So like in the homework that you just finished, we had golf training group as a predictor variable. Is there an effective group on golf score? To answer that question required estimating 3 separate slopes to get up to 6 possible mean differences and to describe what happened. So we went through all of this process of looking at f and R square and the significance of each slope, and then getting linear combinations of slopes to give the differences among the non-references groups. All of that is still tied to one idea of just group. So in the slides that I just made here, I have this sort of phrase several places, like conceptual predictor variable. That's what I mean. It's the idea of like, when you have a research question, how does group predict outcome, for instance? Group is one variable conceptually, but it may take more than one slope to describe its effects. Just like if I wanted to know how age is related to golf scores, if age doesn't just have a linear effect, if it has, say, a quadratic effect too, then the effect of age is two slopes. So same type of idea. So where we're headed in this unit, then, is to where most people need to be eventually to answer any real research questions, which is what happens when we combine more than one conceptual predictor variable into the same model. So we let predictors that are related to each other fight it out to see which still have significant effects after we adjust for the contribution of the other. So this requires a new set of vocabulary, as well as a new method for conveying effect size. So what we would say before is that all of our relationships were reflecting what's known as a bivariate relationship, meaning just two variables at a time. Now, once we have more than one predictor variable in the model, the relationships will indicate their unique contribution. So to me, there are many different ways to describe this using synonyms you would have heard. Adjusting for, controlling for, holding constant, after factoring in, all of those words to me can be said more succinctly as unique. Like, what does this predictor bring to the table uniquely in predicting this outcome that none of the other predictor variables do? Its slope in the model is going to indicate that for you. So because of this controlling for, factoring in adjustment process, the standardized slopes that we might get are no longer going to be the same as just a Pearson's correlation. And we have several different choices as to how we would quantify the effect size of that unique slope. So that's the big picture of where we're headed. So questions so far? Now everyone's quiet. We're good? Good so far? Ready for this? Zoomers, are we ready for this? No? Okay. I'm looking for something. I've got one person in like 20 black boxes.
Yeah.
And the rest of us are all in masks. And so it's hard to tell, right? We're good?
Yeah.
We're good. All right. I was talking to a former student the other day, and I said to him, I'm getting used to teaching in a mask. And he's like, oh, I actually like it better. Because then when my students say, is this going to be on the test, they can't see how irritated I am. It's like, but you still have eyes, right? Like, unless you're wearing like an actual mask or something too, but yeah. But it's hard to tell. So, forgive me for going over the top to make sure that we're all here. I don't want to leave anyone behind. But I do want to talk about one of my favorite TV shows. Because as the most boring person in the world, whose hobbies include television and sleeping and data analysis, I thought, why not bring them all together? Now, rest assured, even if you don't watch this show, you'll be able to follow my example. I'm just borrowing this family. So the show I want to talk about is called This Is Us. It's been on for 6 seasons, and it's in its final season right now. It comes on Tuesday nights, I think, although I only watch it on Hulu, so I have no idea when regular television happens. Am I recording? Yes, I am. Thank you for asking. I am recording. So for those of you who are not familiar, well, actually, let me take a show of hands. Anyone likes this show?
I don't watch it, but I know what it is.
You know what it is?
Yeah.
Don't watch it? Never seen it? Zoomers? A couple people? Not too many? Okay, that's fine. Trust me, you'll still get the example even if you don't watch the show. But the premise of the show is this family, the Pearsons, which are labeled here. So we've got the dad, Jack, and Rebecca, and then they have their 3 kids, Randall, Kevin, and Kate. And the show travels back and forth across time. So it starts when they're like this age, when they were turning 37 or so, and then it goes back and forth with them and their little kids and then teenagers. It goes into the future, and it's always like these cliffhangers because like at the first season, we learned that by the time they're this age, Jack is dead. But he's here in the younger picture, so it's like, at what point did he die and what happened to him? Turns out a crock pot got him. That's what happened. He plugged in a crock pot and it caught their house on fire. And he died in the house fire trying to save Kate's dog.
Oh.
I know. Kate feels very bad.
Yeah, so that must be
Yeah.
Kate vulnerable.
So question, how were the parents the same age as when their kids were little? Yeah, I know it's a spoiler. It happened 6 years ago, so I don't think I'm spoiling too much, but so it's interesting because Mandy Moore is like, I think she's maybe 4 or 5 years younger than me, maybe, but she's actually younger than her children are, like, because when they're this is like a cast photo, but she's like their mom here, and then now when they're this age, she's made up to be like an old lady. So she's really good at being like all the different ages, I think. But anywho, so the premise though is that we have these 3 children and their parents, and these 2 are twins, and Randall is adopted. They were supposed to have triplets, and then one of the triplets died, and they decided to adopt Randall when he was at the hospital at the same time, and it was fate, and now everybody's part of the family here. So this is the story from my regression model, the Pearsons. So let's say, just as a hypothetical here, that Rebecca, the mom, has had it with the messy teenagers. So this is back when they were like 11, 12. And she wants everybody to clean the house. So she has decided to give an incentive. Let's say the Pearson house has 10 rooms that could potentially be cleaned. Everyone has their own bedroom, 2 bathrooms, living room, kitchen, dining, and garage. Let's say that her incentive system is that for each of the people who are going to clean the house, the 3 children and Jack, that you get 1 new Nintendo game for every room that you clean by yourself. Now this is big. By the time, and the context of when this was happening would have been like when Nintendo was first a thing, like Super Mario Brothers and Duck Hunt and all of those sorts of old games. I remember that was like the biggest smile I had ever seen my little brother make, was when he saved up enough birthday and Christmas money to go get his first Nintendo. And he beat Super Mario Brothers like 8 hours later or something, and then had to save up enough money to get another game. But anywho, so she's offering a deal to incentivize each person to work hard at this task, and she's offering a bonus, that if at least 8 out of the 10 rooms get cleaned, she'll buy a new TV for the house. Clearly she values cleanliness in this example. So she decides to let them figure out who's going to clean what. She goes out shopping, she comes home, she wants to figure out what happened. So here's a chart as to what I predict would happen, given my knowledge of the Pearson characters. 9 out of the 10 rooms are clean. No one did the garage. So that meets her standard for the family bonus of getting a new TV. Hooray! But now how do we allocate Nintendo games for each person's individual effort? Well, let's start with Jack, Kevin, and Kate, who both cleaned their own bedrooms. No one else cleaned the master bedroom, Kevin's room, or Kate's room. So unambiguously, they should each earn 1 Nintendo game. Hopefully they'll plan together and not buy the same game, because that would be sad. But that much is clear. But then we have Randall here. Now Randall is an overachiever in childhood and in adulthood. So of course he's going to go above and beyond. He's going to clean 3 rooms. He does his own room and the 2 bathrooms, and no one else helps him, so he gets 3 Nintendo games. But now what do we do about the rest of the house? All 3 of the kids claim that they cleaned the living room. So we don't know who gets the Nintendo game. There's no way to be fair about that. Now, if I had to guess, I'd say Randall did it, and the others like walked in and like fluffed a pillow and called it good or something. But that's just my knowledge of the characters. And the same thing happens with the kitchen and the dining area. Jack claims that he did that, but Randall said he did that too. So these 3 rooms do not yield an individual reward, but yet they overall contribute to the amount of rooms that were cleaned as a composite. No one gets credit for the 3 rooms that multiple people cleaned, but they do contribute to the family winning a TV by cleaning at least 8 rooms. So this is my way of introducing the idea of common versus unique prediction in multiple regression. The way that it is normally described is by a picture that looks like this. So this type of image I know of as a Venn diagram. Another word for this I've seen is ballantine with a B. Yeah, that was in the textbook, but I call this a Venn diagram. The idea of overlapping areas. So this type of diagram, back to our regular stats course, by the way, although the Pearsons will show up later again. Let's say that y is the blue circle here, x1 is one of the predictors, and x2 is another predictor. So we've divvied up the areas of y in such a way that we're describing sections or partitions of its variability and how it relates to the two predictors. So A is the part of y that x1 is related to uniquely, that x1 is related to, but x2 has nothing to do with. B is the part of x2 that's related to y that has nothing to do with x1. So like A would be the rooms that x1 cleaned that no one else did. B would be the rooms that x2 cleaned that no one else did. And C is for common, are the rooms that more than one person did, so we're not sure who we should give the Nintendo game to. And E is what's left. In your textbook, they have a picture like this, and they put D there for continuity, but I'm going with E, because what I mean by E is residual, just like in the equations. So E is the part of the y variance that is unrelated to either predictor or what they have in common. It's residual. So in the Pearson example, E would be the garage, the room that didn't get cleaned by anybody. Okay, with me so far? All right. And the punchline to all of this is that if you learn how to do data analysis, you can earn enough money to pay someone to clean your house. So general utility is one thing we want to know about this. How well do the predictors work together to predict y? So from a everyone pitching in standpoint, how clean can we make this house? How well can we predict y with our combination of predictor variables? So that question is answered in the exact same way that you're used to thinking about with respect to the model f-test and the r-square. Is the r-square significantly greater than 0? We answer that with an f-test, which is a ratio of sort of known information to unknown. And if the answer is yes, then yeah, the areas A, B, and C here are not 0. And we can use r-square to quantify just how much that is. So in terms of the picture, the model r-square would be formed with everything that's not E in the numerator and the total variability from all 4 areas in the denominator. So the way that I drew this picture, I'd say that E is maybe 25%, give or take. I'm not an artist, but that's my best guess. And the other 3 work together to capture about 75%. So these are in percentages that are analogous to squared units. So these are in variance terms that we're talking about here. So that's one thing we want to know, is how good is our model? How well do the predictors work together to get the house clean? But then, how much effort did each individual cleaner/predictor put forth? So what's the specific utility? And here's the tricky part. Each predictor is only going to get credit, so to speak, for the amount of variability that it uniquely predicts in y that no other predictor did. So best case scenario is you would have 2 cleaners who decide ahead of time which rooms they're going to clean. There's no overlap. That way they each get credit for everything they did. So 0 correlation between predictors would be optimal for trying to get the largest effect per predictor that you can. And that is the logic by which in experimental design, people might randomly assign people to groups, and then within each group randomly assign to some other variable, so that the 2 variables are completely uncorrelated, and each can show its full effect in predicting an outcome. Now, if we're dealing with observed data, most of the time the predictors that we care about are going to be related to each other to at least some extent. So then the question is, what does each uniquely bring to the table that the other doesn't? So this area C, that is in common, the rooms that more than one person cleaned, that's going to contribute to the model R square, but it's not going to show up as part of any individual predictor's unique effect. So worst case scenario is if you had X1 and X2 that are almost completely correlated, it could look like neither of them does anything because they have so much in common that only the common part is actually what's doing the work. So we're trying to weigh sort of two different things at the same time. Common is still helpful for the R square, but common is not helpful in deciding how strong of an effect each predictor has. Okay, how are we doing? Hit me.
So, in terms of Jack, Kevin, Kate, are they the ABCD or, I mean, I'm not conceptually getting whether they're X or A.
So Y is the house. X1 is going to be, let's go with Randall, and X2 is going to be Kevin. And I need more circles for the other people.
Okay. Thank you.
Sure. So A would be the amount of the house that, say, Randall cleaned. B is the amount of the house that Kevin cleaned. C is the amount that they both cleaned. E is the amount that didn't get cleaned at all by anybody.
And we don't know if C is true.
Well, we can know that. We will know that if we look at how related X1 and X2 are by themselves. That will give us a basis because they have to be related at all for C to be possible. But then what's harder to anticipate is how much of their common relationship is also shared with Y. So there's like a common intersection of 3 variables here, not just 2. And so that's what modeling is going to tell you, is basically how much is unique versus how much is common.
Can you say what the 3 variables are?
The 3 variables in the story here are X1, X2, and Y.
Okay.
And so C is the intersection of all 3. So area C is not just what X1 and X2 have in common, but also what they have in common that's related to Y. So like this little part down here is where they also overlap, but it's outside the blue circle. So that's what they have in common that's unrelated to Y in addition. Yeah, it gets complicated quick. But this is 3 variables because that's what I'm capable of drawing. Okay, other questions from the Zoomers? Watching the chat window, or you can talk. All right. So then let's go through how the story changes when you have more than one predictor. First off, how you would describe the model. Let's say that I have X1 and X2 in the same model. So now beta 0, expected outcome when my predictor is 0, when both predictors are 0. So doubly conditional in this case. It's 0 on X1 and 0 on X2 simultaneously. Beta 1 is the slope of X1. Rather than just saying it's the change in Y for a 1-unit change in X, I would say that it's the unique change in Y, or the difference in Y per unit X. And so other ways that you'll see people describe that word unique is controlling for, partialing out, holding constant, adjusting for. After factoring in X2, what does X1 bring uniquely to the prediction of Y? That's what beta 1 is telling us. So whenever X1 and X2 are related to each other, their effect sizes for prediction are going to be different than what they would be for just a Pearson's correlation. Not the Pearsons on TV, the old dead guy Pearson who made all this stuff up. Different person. Perhaps related, but Pearson is a very common name, so I'm not sure. So I have a note here that beta 1 is still assumed to be constant over all values of X1 and X2, meaning that this beta 1 slope is thought to apply to everybody, regardless of their value of X2. It's just that it's the X1 slope after adjusting for the contribution of X2. So beta 1 would be reflecting area A only in the previous picture here. Likewise, beta 2's slope or beta 2 for the effect of x2 is reflecting area B in the picture, and it's the unique effect of x2 after controlling for x1. So in practice, I don't think every single sentence in your results section has to say it this way. I think it's enough at the beginning to say, you know, the model slopes are all conditional on, you know, after controlling for every other predictor in the model, and then you can just talk about it. And so beta 2 then is assumed to hold to everybody. So beta 2 is the slope for everybody regardless of their values of x1, but it's reflecting the unique contribution of x2 after factoring in x1. So I make that distinction because our next unit is going to relax that constraint and examine the idea of multiplicative effects rather than additive effects, whether the effect of x1 varies as a function of x2 or vice versa. That idea, by the way, is called moderation, and that's what we're doing next. So for now, additive effects. I have this slide in here just in case you've been reading the textbook, and they talk about how some of the way that the slopes can be formed on the basis of correlations and covariances. The point that I want to make, though, is that in the 2 predictor model on the bottom, the orange boxes, that's the new part. The standardized coefficient that describes the unique effect of each predictor starts out with the correlation between y and that predictor and then literally subtracts off a function of what they have in common. So it subtracts off the correlation of the other variable with the outcome times the correlation between the 2 predictors, for instance. So the idea of adjusting for or factoring out is taking that part of the prediction away so that only the unique part remains. And if we look at different ways of describing how the model R² changes in the function of more than one predictor variable, here's the old way that we talked about it, how R² for the model is the square of the R between y hat and y. We can also think of it as the proportion of variance that's explained by the model, or the reduction in the residual relative to the total, either way. So here's a couple different ways that I've seen people describe how R² is computed in the context of more than one predictor. And again, the point I want to make is the orange boxes here. The part that is being subtracted off is a function of the covariance in the first box, but then the part that is being added is a function of the covariance between the two because they're starting with the standardized effects for the unique. So you can think of it either way. The point is that the model R² has the common part in it. Even though no individual predictor gets credit for what they both overlap in, the R² does give the credit. Question, is that like finding A by subtracting B and C from E in the diagram? Yes, exactly. You can start with total and subtract off common, or you can start with unique and add on common, either way. The other piece of this then is that what we do with the standard errors also has to change to reflect this idea of unique versus common. So where we had standard errors from before, on slide 14 on the top here, this is what the formula for a standard error of a slope is if you only have one slope. The numerator is residual variance. So all things being equal, the better your model, the less residual variance you got left over, the smaller the standard error is going to be for any one predictor. That's still true. The denominator is a function of sample size minus the number of fixed effects. This term right here has a special name. Anyone remember what that is? N minus K? Say it louder. Denominator degrees of freedom, yes indeed. So all things being equal, more people, smaller standard error, because the residual variance gets divided by more, makes it smaller. And then because we're dealing with units, so a slope is the change in y per units of x, units of y show up in the numerator, so we need units of x to show up, and that's the variance of the x. So that part just makes sure the scale works with respect to what the standard error size should be. If you change the scale of x, the standard error has to change with it. Once we add in more than one predictor at the same time, we get a new term in the bottom. So we have the variability of x is now going to be multiplied by this function 1 minus r squared for x. That is the amount of variability that x has uniquely that is not predicted by the other predictors. So it's not just the variance in x, but the amount of unique variance in x that matters. So that adds then a further condition with respect to when the standard error would be smaller. The less unique variance you have, the bigger the standard error. So if we look at where these things show up in the equation, less residual variance, that means smaller standard error. So practically speaking, if you have a list of predictors to add to a model, and let's say you put in one, it's not significant, so you take it out. You go down your list, you add a bunch in that are significant. That first predictor, if you re-added it later, could actually be significant later because the residual variance is lower than what it was initially. So that's part of the reason why going through a process of adding predictors sequentially can sometimes lead you astray, because the decisions that you make are predicated on the order. And if you reordered it, you might end up at a different place. All things being equal, more people, smaller standard error, more power. So why we care about standard errors is because they are what our slopes get divided by to make our test statistic. So smaller standard error means more likely to have a slope be significantly different than 0. So the new part then, the less unique variance the predictor has, the higher its standard error is going to be. And that makes sense if you think of it intuitively. If two predictors are highly related to each other, and each doesn't have a lot of unique information, it's going to get really hard to figure out what each brings to the table because they have so much overlap. Okay, how are we doing? 246, hanging in there. Any questions before we keep going? Or clarifications? All right. Foreshadowing what I just said, it's like I put the slides together. I knew this was coming next. And in fact, I put these slides together over the weekend because I decided to retool this lecture quite a bit. So it's fresh in my head. So in terms of the four-step process we talked about before, revisiting that sort of idea. So when you have research questions and a data set with which to answer them, step 0 is to figure out how you're going to put your predictor variables into the model. So if it's a quantitative predictor, that involves centering so that 0 is a meaningful value. That makes sure that your intercept stays an interpretable value. For categorical predictors, you would have to decide how you want to represent the differences between the categories. So usually that involves some sort of dummy coding scheme where you would create as many new variables as you have categories minus 1. Indicator coding is recommended for variables that are nominal, so where you have one group versus each of the others. Sequential coding is like the piecewise version we did at the end of last week, where you can look at adjacent differences among ordered categories. So that's sort of something you have to decide based on what the variable means, what you want to know about it, and how it's measured, what would make sense. Step 1 then, after we have our variables to work with, would be to examine bivariate relationships. So this is what we've been doing up to this point. Where bivariate, a synonym for that, by the way, is 0 order. You'll see that written. I'm not sure why, to be honest, because it doesn't seem to make sense, but that's what it means. Bivariate means 2. I know that much. So just what does each predictor have in common with y to start with? Like just answer that question, figure that much out. So if you are dealing with a quantitative predictor that only has a linear relationship, or a binary predictor in which it can only have a linear relationship, you can get a correlation matrix to answer this question. So you can look at a matrix of correlations across multiple variables at the same time. It's very convenient. That type of summary information is almost always reported in research study results sections. It starts to break down, though, if you have predictors to include that don't just have linear relationships or aren't just binary. Then Pearson's correlation actually doesn't work, because it looks at each variable separately and doesn't understand how they're to work together to represent the overall total predictor. So in that case, you need a model. So like what we did in the last unit, looking at a 3-category work group, quadratic age, piecewise education, those are all instances in which the total relationship between x and y is represented by multiple slopes, and so you need a model to be able to characterize that. And so then you can look at the relationship as amount of shared variance via the model R² rather than just the square of the Pearson correlation. Ideally, I have to admit I don't always do this, but ideally you'd also want to look at bivariate relationships among your predictors. And which you would do it in the same way, model if anything's not linear or binary. But what you're looking for is how related they are with respect to competition in predicting the outcome. So if you have 2 predictors that you're interested in examining, but they're correlated 0.9, that's not going to go well. A correlation of 0.9 is almost perfect. That means that if I square that correlation of 0.9, that's 81% shared information. So they don't have a lot of room to each have an individually significant prediction. So knowing that ahead of time may change your strategy. That strategy, step 3, should be guided by your research questions. So here's a couple examples of what people tend to do. One type of research question is more straightforward. You might ask, how does y relate to these 3 predictors? Okay, put all the predictors into the model. You can report the model f-test for the significance of the R², how much variability it accounted for. You'd also talk about the direction, significance, and effect size of each predictor. And I'll tell you more about effect sizes in just a little bit here. And you write it up and you turn it in. Alternatively, and how I often see research questions being phrased, it seems to lend itself to a stepwise process. So for instance, specific aim 1, after controlling for x1, how does x2 predict y? So after controlling for socioeconomic status, what is the relationship between this child characteristic and this child outcome? Something like that. Then, after controlling for x1 and x2, how does x3 predict y? So you can get sort of these layers of incremental prediction. And to answer the question as it's written, what most people would do is what is often called stepwise regression for this very reason. So I'd put x1 into the model, talk about what happens. That means its direction, its significance, and its effect size. I would then add x2, keeping x1. So the keeping x1 part is necessary to answer the after controlling for x1 aspect of the question. It has to stay, even if it's not significant, by the way. Then I would look at the change in the model R². So this is something that we haven't done directly yet. This is something new for this unit. An f-test to assess how much better the model got after adding something to it. All we've done up to this point is how much better is the model than the empty model, like going from nothing to something. This is like something to something more. So then we talk about what happened with x2, its direction, significance, and effect size. If it had more than one slope to it, then that's not going to be redundant with the R² change test. And then we might also talk about what happened to x1. So after adding x2, is x1 still a significant effect? We might talk about that too. And then to get to the second part of the question, we'd estimate a third model, adding in x3. say what the change in the prediction was, say what happened to x3, comment on all those things changed. So this is a very common type of strategy. However, I would encourage you to have caution in applying such a strategy. Here's the thing. This type of hierarchical strategy is predicated on there being one set of ordering of predictors that makes sense, that no one would disagree with. That is rarely the case in observational data. The reason that people do it this way in separate models is because that's the way that they've learned how to get the change in the R-square. Well, I need to know what it was before, and now I'll add something and see how much it went up. That seems intuitive. But what if I told you that I am going to teach you how to figure out what the change in R-square would be for everything all at the same time? Basically, what would happen if I dropped this thing? How much worse would the model get? You can do a test for that. What would happen if I dropped this other thing too? So you can have a simultaneous analysis, but still answer these types of sub-questions as to what is the unique contribution of each predictor. The advantage of doing it in a simultaneous way is that you don't run into the situation where having a predictor show up first somehow penalizes it relative to showing up later. If you go through a process of adding in predictors and you drop them if they're non-significant, then which way you added them in is going to matter, because you may end up dropping things if it's entered first versus later. There are, by the way, automated routines that will do this for you. So there are automatic forward selection, backwise selection, et cetera, things you can do in software where you feed it a set of predictor variables and an outcome and say, find it. I'll be back in an hour. And when you come back, the most optimal combination of predictors is there. Now, if your only goal is to predict the outcome and you don't absolutely care why or how, that's a reasonable strategy. But if you're trying to do theoretically driven research, then letting the computer figure out which predictors should be there is not going to be defensible. So there's a big difference in using these sorts of prediction models solely for the purpose of prediction, and I don't care about the theoretical mechanism, I just want to predict this thing, versus I'm using prediction models to make theoretical statements about the relationships in the world. So if you're in the latter camp, which is what most research is, then I would caution you from letting these routines figure out what your model should look like. The I don't care what happens, I just want to predict it is related to things like machine learning and data science, where you're the CEO of Target and your only objective is to get people to shop at Target and spend more money there. So you mine all of the credit card receipts and the shopping points and all the other things they do to track your data so they can send you targeted ads when you're scrolling through Facebook about what you're missing from Target and what's on sale this week. Like their only objective is to buy. They don't care about the mechanism. That's a different type of problem than I'm going to make statements about the world. Okay, so here's a thing. When you go to start publishing papers, you'll see what my husband and I refer to as the angry reviewer checklist. Like just certain things that reviewers are just going to complain about because it's like they're going down a list. And one of them is missing data. That's an easy one. Small sample size and lack of power. That's another one. And one that you'll often see is multicollinearity. See also multicollinearity with 2 L's, or just collinearity with 1 L, or collinearity with 2 L's. I've seen it all 4 ways. What that word means is that your predictors are related to each other. Okay, and the fact is, if you have predictors that are highly related, they have a lot in common. The more they have in common, the harder it's going to be to figure out what they each uniquely bring to the table. Okay, that's a mathematical consequence of relationships that exist in the world. So knowing that ahead of time doesn't necessarily change how you would approach this process. So you will see statistics that you can output, something called tolerance, which is the amount of unique predictor variance. So that's related to the standard error, obviously. Or you'll see the reciprocal of it as a variance inflation factor. And you may see guidelines in textbooks as to what is bad. So this is what the reviewers are worried about. Oh, I want to see the tolerance on that because I think it's too high because you have multicollinearity. Okay, what's the problem? Well, it's just, it's bad. I learned it was bad. And that's kind of the end of the thing. Now, once upon a time, when computers were not as good as they are now, this could have been a legit problem because you can end up with a lack of stability when basically numbers can go crazy. That's not a thing anymore. Only when you have singularity is it truly a problem. And that means complete redundancy. Oftentimes, that is a result of somebody screwing something up. It is rare that you would find completely redundant predictors otherwise. But here's a way that you can screw this up. Let's say that you have scale scores, and you're dealing with an instrument that has multiple possible subscales to it, and you decide that it would be a good idea to put in the subscales and their total as separate predictors. It's redundant. There's nothing that the total can do that the subscales don't already do. Likewise, I've seen a couple of instances of these, of people who are getting used to doing dummy coding. If you put in the original 4-group variable along with your 3 dummy codes, or if you have 4 groups and you make 4 dummy codes by accident and you put them all in with the intercept, then you have 5 fixed effects to describe 4 things. And one of them is going to be eliminated from the model because they're redundant. So you will know when this happens because in your output, instead of numbers for a given slope, you will get a row of dots where it's like, meh? That's a problem. That means that something is screwed up. Maybe you accidentally overrode a variable with another variable, and so you have the wrong information in the analysis, or otherwise you screwed up something that's on your end. Question?
Yeah, so if 2 things are very closely related or redundant, I was wondering on an outcome level or on the residual level, does it show double the effect or does it show the same effect but with 2 predictors, which could have gotten with just 1 predictor?
If 2 things are highly related, what they have in common will count once towards the R-square rather than twice. So some of the R-square formulas have like a 2 to it for that adjustment. And what they each contribute individually will form the basis of its slope. So you can be in a situation where you have, say, 2 predictors that are very related to each other and they're very related to the outcome. You can have a significant model R-square, meaning that the model works, they work together, but when you look at the p-value for each predictor, they're non-significant. And it's like, wait a minute. How can I have a significant model if nothing is contributing to it significantly? And the answer is because of what they share in common. So if your goal is prediction, that's not a problem. You're like, okay, I don't care what's doing the predicting so long as I've got prediction happening. If your goal is to make a theoretical statement about how construct A is different than construct B and how it relates to construct C, then you're in trouble. But there's nothing you can do about it. They're just related. So in your earlier process of looking at step 2 here, examining bivariate relationship across all the variables to be considered. If something is super highly related, you just want to know that those 2 variables that are super highly related are probably going to cause problems for each other. But it doesn't necessarily mean that you would dump them. What you might do instead is consider the possibility of alternative models. So for instance, I helped with a grant proposal recently where there was a gold standard of measuring some sort of biological phenomenon that required invasive blood draws that nobody wants to do. And the principal investigator was proposing to replace this measure with something that was less invasive and easier to get and less painful. So the question is, if these 2 things are very highly related, to what extent could I swap one for the other? That's an equivalent models question. So a different way of thinking about a collinearity problem is, okay, can I swap these two things that are super related, or does one actually do a better job? And that type of question requires that they be put in separate models and let the model then determine which is the better answer, if you can only have one or the other. So this would be a question requiring a comparison of what's known as non-nested models. I don't think we've introduced this terminology yet. Is that right? Is non-nested a word you've heard before? In statistics, the word nested means like 17 different things. So it completely depends on the context what it means. But in this case, we're talking about whether a model is a subset of another or not. So a nested model would be something like, I have a model with just A in it versus a model with A, B, and C. If I do a comparison of these models, what I'm asking is, what do B and C bring to the table? Because that's what makes them different. Most of statistics is phrased in that way because we have very ready techniques for answering that question. Non-nested models is what I'm talking about here. So if we know that we need A, and the question is, if B and C are super highly related, which should we pick? Then what I would want to do is compare a model that has A and B versus a model that has A and C. The one with the higher R-square wins. But not just numerically higher. I would want to know if it's significantly higher. And there's a technique for that known as Hotelling's T. And it's based on outputting the y hat predicted by each model and correlating them and using that as part of the test. So there is a way to do that. There's also a section in your textbook on something called dominance analysis, which is related to trying to figure out which predictors bring the most to the table when there's other predictors that also have a lot of, that they have a lot in common with. That's not something I've done a lot of, but I wanted to point you towards that resource. The other thing that you can try to do to address multicollinearity, if you're not interested in specifying separate models, is just to hack it. So if I go back this. The residual variance of y, the smaller that gets, the smaller my standard error is, the more power I have. So one strategy for fixing multicollinearity, which is when standard errors are too high because each variable doesn't have enough that's unique to it, is to try to reduce the variance in y. So for that reason, you might consider putting predictors in your model that you don't even care about, that have nothing to do with the predictors you do care about, but you're putting it in because it has to do with y. The less leftover variance there is in y, the smaller the standard errors are for every predictor in the model, care about or not. So if you are trying to predict, the difference, say, let's say you're doing like a clinical trial or something, and you want to know if a new medication works better than an old medication, and your outcome is some sort of measure of sickness, put everything in that's related to sickness. Suck up as much of that extra variance as you possibly can, and then you'll have the most powerful test for the thing you do care about. There is a design of experiments is a class that I would recommend to anyone who's finishing this class this semester to be offered in the fall. It's by Ariel Aloe, and he talks a lot about this idea of how you can improve the power from design and thinking about what covariates to include beyond just the predictors that you're interested in. So that would be a good next step for those of you who are planning your fall classes, learning more about this type of thing. Okay, how are we doing so far? So-so? Is this making you think of any research that's going on in your other worlds? How this applies? Research questions? Maybe? Anyone you want to play with? Free consulting advice. This is your chance. I charge big bucks for this outside the classroom, so you get it for free, I know. For the bargain price of out-of-state graduate tuition, right? Free. No, but in all seriousness, I really do like it when people bring up things in class from their own personal worlds, because then I have another set of examples that I can pull from to talk about. So if this is making you think of anything and you want to share with the group, Definitely want to hear it. I'll let that percolate. So what's next? Oh, effect size. Yeah. So it turns out that effect size is super tricky in these models because there's different ones and they mean different things, and people are not always clear what they have. So I want to introduce you to what the possibilities are and what the differences are and what they tell you, so that you can decide for yourself which one is most useful. So all of these slopes that we're talking about, we can look at their direction and we can say, you know, as x goes up, y either goes up if it's a positive slope, or as x goes up, y goes down if it's a negative slope. We can look at their significance tests and say, how likely is it that we found a slope this big if the true slope were 0? That's what the p-value tells you. But then we have to figure out how to translate that into how big is this relationship really? And the latter part is tricky because these are in units, right? It's in years or pounds or dollars or something. And it's like, well, the slope is going to be bigger because of the variables that it's working with. If you change the scale of your variables, you change the slope, even if you don't change the significance. So we need effect size. So the trick is then, what kind of effect size do we want to use for a unique effect after controlling for the other predictors? So this is going to be relevant potentially per fixed slope as well as per conceptual predictor. Now, what do I mean by conceptual predictor is the idea that one variable takes multiple slopes and we want to link them together somehow. So like if I have golf group for homework, I take 3 slopes to describe the effect of golf. So I want an effect size for the 3 slopes combined because that's the effective group in my story. If I have linear and quadratic age, I want to get an effect size for their contribution combined because that's the effective age in total. Why is this useful? Beyond just conveying effect size, it's helpful for other people. So meta-analysis, are you familiar with this term? Research synthesis or meta-analysis? It's the idea of doing a study about studies. So is screen time bad for children? I really hope not, because mine loves screens more than he loves life itself. But if I wanted to answer that question, I could go through and look at different research studies that have looked at the relationship, say, between hours of video gaming and children's outcomes, hours of TV and children's outcomes, and I'm sure I'd find lots of studies. A meta-analysis would take the effect sizes out of each of those studies and make a data set of those effect sizes, and then analyze that data set of effect sizes to try to figure out why some studies found stronger effects than others. So do you get more relationships between screen time and childhood outcomes in younger children than older? Or children from this background versus that background, or something like that? So people who are doing meta-analyses need to have effect sizes from your study in order to do that. So you're doing them a favor if you provide effect sizes beyond just conveying the size of your effects. The other people that you're helping are the people who are going to follow in your footsteps. How many people do I need? Well, I don't know. More. The answer is always more. Well, where do I get even a sense of where to start? Go to the literature. Figure out what effect sizes you're looking to have power for. Then you can work backwards to figure out what a reasonable sample size would be given the going rate of effect size in your field. So if you're from an area that has very small effect sizes, you're going to need more people to have a shot at finding them reliably than if you're from an area that has huge effect sizes. So the people who are following in your footsteps want you to give you effect sizes as well, and to be very clear about what kind they are. Now here comes where the unclear part is, and this is what we'll get into next time is, oh my God, the alphabet soup of these things. So you've met R before, right? Correlation R. You're going to find a synonym for R, which is eta, which is this Greek letter right here that looks more like N than R. Eta means R. Likewise, eta squared is analogous to R squared, but not all of them are ratios. Generally speaking, effect sizes are going to come in one metric versus another, whether it's in a correlation metric or a correlation squared metric, and then whether or not they are the adjusted sample size version or the unadjusted version. So you can think of it as sort of a 2 by 2 table. And then there's this other thing, which is Cohen's F squared, which is a squared thing, but it has little to do with the others. But I'm throwing it in here because people use it for power analysis. So where we will go next time then is trying to figure out what these things are telling you, and more nefariously, which ones are adjustable by researcher degrees of freedom and which ones are not. Dun, dun, dun. See, I'm trying to be dramatic here. I know. Oh. So I had a student once this semester put a screenshot in an email and say, what is this thing? Because this had an eta squared in the paper, and all it said is that it was an eta squared. Not what kind, what it meant. And I'm like, I don't know what it is either. You got to be more specific. So that's what we'll do next time. So, any questions before we call it a day? Yes.
I have one confirmation question that if we have 5 predictors such as x1, x2, x3, x4, x5,
Mm-hmm.
and then I want to control for x3, 4, and 5,
Mm-hmm.
then the outcome is the combination of x1 and x2, or
They all control for each other if they're all in the same model.
what does it
Meaning that if you have 5 predictors, each one is the unique combination after taking into account the other 4.
the other 4.
Mhm.
So the predictor should be just one, not a 2.
You can have as many as you want. You can have up to degrees of freedom, n-1 predictors. I'm not sure I'm following your question, but let's talk after class for just a minute so I can say goodbye to everybody. And thank you, because it's garbage day, which means I say see you Thursday. And let me know if you need anything.